Good morning, guys. Today we're going to look at sampling distributions of sample proportions. Similar to the example we worked last time, but more specifically, what are the rules if we're dealing with categorical data, so dealing with proportions. So a sampling distribution is a quantitative distribution, so it has a shape, it has a center, it has a spread, and that's what we're going to focus on. What are the characteristics for all sampling distributions for a proportion, for sample proportions? And then the next lesson we'll talk about dealing with sample mean. So this shape. So if we think of a sampling distribution, a sample proportion as a binomial distribution, right? If you're dealing with proportions, something either happens or it doesn't happen, because you're talking about how often something occurs. So it either occurs or it doesn't occur. Well, we can think of that as a binomial situation, right? So if we think back to our binomial distributions, whatever the probability of that specific event occurring, that was our most likely outcome. So that's what we're talking about. So if I'm dealing with what proportion of a group has red hair, for example. So when I look at doing a lot of different samples and getting a lot of red-haired proportions, each one of those is a binomial distribution. You know, what's the probability that 6% of the population has red hair? What's the probability that's 7%, so on. So that's what I mean by binomial distributions. So when the sample size is small, then the sampling distribution of that sample proportion takes the shape of that corresponding binomial distribution. So it is a binomial distribution. How many red-headed people were in our sample, for example? So were there 0, were there 1, were there 2? What were the corresponding probabilities to each of those possible outcomes? So when that sample size is small, it's just going to look like the binomial distribution that we worked with before. However, as sample size increases, so say I'm not looking at 5 people in my sample and counting the number of redheads. I'm looking at 10 people, or I'm looking at 20 people, or I'm looking at 70 people. So the more people I look at in a sample, the sampling distribution, meaning all possibles of size 20 or 60 or 70, as that sample size increases, then the sampling distribution of sample proportion becomes more symmetric. So we stop seeing those little bitty tails out toward the edges, and we get concentrating on what's going on around this around this typical value, this expected value. So it becomes more symmetric, and that graph takes on a more normal shape. So for example, when things are small, we could get a sampling distribution that looks, so say the center is around like 0.20 or something like that. It may look like that. It may really just drag out here to the right and really drag on out here to the right. So I say this is something that only occurs 20% of the time, right? So 20% of the population is redheads, or something example like that. If we do larger samples, so samples of size 50, 60, 70, 80, 100, I don't know, however many, 50. If I do large samples, then it still should be centered around that 20%, just like it was here, but we don't see those little tails. It compresses and it becomes more symmetric and more normal. That's what we're saying right there. That's the effect sample size can have on the shape of the distribution. Well, why is that useful to know? Why is it useful to know if I'm dealing with a binomial distribution or a normal distribution? Well, it goes back to what we talked about with probabilities. Binomial probabilities are a lot more difficult for us to calculate a lot of the time than normal probabilities are, because those normal probabilities are just throw it in the calculator, normal CDF. Binomial probabilities, when you're dealing with a less than, greater than, those inequality statements, those calculations get a little more complex, even with the calculator. A little more we have to think about. So we like to use normal distributions when we can use normal distributions. So we should design our studies realistically to get us into those normal shapes for these sample proportions. So to use a normal distribution approximation, so normal approximations for a sampling distribution of sample proportions, we must meet the large counts condition. And this is what we talked about before with binomial distributions. We talked about when we did binomials that the larger your sample size, the more events that you're looking at, the more normal it becomes. Well, that's why we talked about that, because we want to use a normal. So if we remember large counts condition, says NP is greater than or equal to, remember this is your sample size times your probability of success. So say 20% of people are redheads, that's all that means right there. Okay, so however many people we sample times the probability of getting the outcome we're looking for, that needs to be greater than or equal to 10, and n times 1 minus p, that's the probability of what we're not looking for. So another way we could think of this is we need to expect at least 10 successes, and we need to expect at least 10 failures. That's what large counts condition tells us. So if I have a large enough sample that we're expecting at least 10 successes, at least 10 failures. So if I'm dealing with a 20% success rate, I need to have at least 50 total individuals, because 20% of 50 is 10, and 80% of 50 is 40. So that gives me at least 10 for what we would expect the redheads to be and the non-redheads to be. So that's what we're talking about for large counts condition. So when you're dealing with proportions, large counts condition says you got to have at least 10 successes, 10 failures expected before you can even try to treat it as a normal. Otherwise, if it's anything less than that, you got to do all your calculations with binomial distributions. All right, so that's the shape of a sampling distribution of sample proportions. Now let's talk about the center and spread. All right, now to the center. All right, now to the center of this sampling distribution. So as we said before, proportions are binomial. So if you're dealing with proportions, if you're calculating proportions, you're dealing with a binomial random variable. So just kind of recapping, the mean of a binomial random variable is just n times p. Right? The expected number of successes is the number of trials times the probability of success. Just redefining what a sample proportion is, p hat is nothing more than your number of successes over your number of attempts. Number of successes, number of attempts. So expected number of successes is this. The way we calculate the proportion of success is right here. Now, x over n, I could really just think of that as 1 over n times x. Right? Just move your numerator out to the side, make it a coefficient. So if I'm wanting this is the center of our sampling distribution, the mu of p hat, the expected p hat. That's all it says. We want to know what the expected sample proportion is for the sampling distribution. Well, how would we get that? Let's just go through and do a little substitution. So if instead of working with mu of x, I'm working with mu of p hat, all I've got to do is substitute what x is equal to in for x on my p hat. So instead of p hat being 1 over n times x, p hat is 1 over n times np, your expected value right there. Now you go through, you do a little arithmetic. 1 over n times n, we notice that'll cancel out, right? So we are left with p. So what we end up with is mu of p hat equals p. The expected sample proportion of a sampling distribution, or center of a sampling distribution of sample proportions, is equal to p. Well, what does p represent? P is the proportion of the population that has this characteristic. So in our case, our expected proportion of people with red hair should equal what's going on in the actual population, right? So the sampling distribution center should equal it. Well, that should look familiar because as we talked before, when that is the case, this is an unbiased estimator. So that's nothing more than the definition of an unbiased estimator. So the center of the sampling distribution is the population parameter. What we see from all possible samples should center out with what's actually going on in the population. Hopefully that's kind of an intuitive type of thing. Right, so now let's talk about spread. Well, spread's obviously going to have some type of calculation to it. I don't think it would work so neatly and cleanly. So let's recap what spread is. So spread, or standard deviation for binomial random variables, was this right here. So sigma of x is equal to square root of n times p times 1 minus p. But that's only if the samples are independent. Let's talk about that independence first. How do I show that the samples are independent? There's two ways we can do it. One way that I can show that the samples are independent is I can sample with replacement. Meaning that take all my individuals out, throw them back, and so pulling one group of individuals out didn't affect the other group, right? Because you have those same individuals. Or the other way we did it, and that doesn't happen very often, the other way we could do it is with that 10% condition. 10% condition. If you guys remember, 10% condition said in our binomials, if the sample is less than 10% of the population, then we can consider our samples independent. So that's nothing more than n is less than or equal to 10% of capital N. Sample size less than or equal to 10% of the population. So that's the way we want to show independence. And we need to get in the habit of showing independence every time. Just like if we're going to work with normal distributions, we need to get in the habit of showing that we've met large counts condition. If we're going to deal with standard deviation at all in this stuff, you got to get in the habit of showing that we have independence first, that we have met that 10% condition. So let's go through and see if we can calculate, instead of sigma of x, sigma of p hat. So just kind of going through that same logic, I want to turn x into p hat. So I'm just going to sub x into my p hat equation. So I get 1 over n equals square root of n times p times 1 minus p times. We can clean this stuff up a little bit. You get this guy right here. Now, through a little bit of algebra, we could, you'll usually see it in a much neater form. If we just squared all of that stuff, so just again, going through algebra, getting squared everything under the square root. Notice that the n and the n squared will cancel. So we end up getting this formula that you'll see most often, where the standard deviation of sample proportions is equal to p times 1 minus p over n, all squared. So square root of p hat, or sorry, standard deviation of p hat is equal to square root of p times 1 minus p over n. Again, I know you love it. It's another standard deviation formula. It's a manipulation of your binomial standard deviation formula on, but just now doing for p hat, which is all sample proportions, or all possible sample proportions. All right, so that's it when we're dealing with sample proportions. Things that we need to key in on. The shape when the sample is small is going to look like the binomial distribution that it corresponds to. The shape of the sampling distribution when the samples are large, meaning we've met large counts condition, is going to be normal. It's going to be more normal, more symmetric. The center of the sampling distribution of sample proportions should match up to our population proportion. And then the standard deviation would be square root of the probability of success times probability of failure divided by that sample size. All right, that's it, and I will see you guys in class tomorrow.